So today I'd like to talk to you about resistance. We've already learned the terms voltage, current, power. We now want to talk about the final important term, and that is the term resistance. Resistance talks about how hard or easy it will be for electricity to pass through a wire. Back in the day, when they were first starting to work with electricity, stringing up telegraph lines from city to city, they realized that their signal would get weaker as it went through wires. And they needed some way to describe how much energy they were going to lose as they sent the signal from place to place. They started out with all kinds of crazy units to describe how much resistance there was in a wire. But eventually, they came upon a unit that everybody seemed to agree was the best way of measuring this property of matter. That unit is called the ohm. It goes by the symbol omega. It is named after a German scientist named George Simon Ohm. And the way the ohm is defined, it talks about how much voltage do you have to apply to an object to get a current of 1 amp to go through that object. So again, you would hook up a battery where you could change the voltage, and you would keep changing the voltage until exactly 1 amp of current went through your system. So an ohm, 1 ohm, is the voltage required to produce 1 amp. So one more time, an ohm, 1 ohm means 1 volt was required to make a current of 1 amp. If you had 5 ohms, that would mean it would take 5 volts to make a current of 1 amp. So the higher the resistance, the harder it is to produce a current of 1 amp. Okay, if you'd like to keep track of your scientist on your scientist sheet, the pink sheet, here is all the information. Again, George Simon Ohm came up with his laws on how electricity worked back in 1827, and again, it is known as the ohm. I want you to realize that there are some cases where you want to have small resistance, and there's other times where you'd like to have a moderately high resistance. So if your wires are trying to bring as much electricity as possible from one place to another, like you're trying to jump your car battery, you want these things to have the lowest possible resistance that you can. You want to get the energy from battery to battery as efficiently as possible. The same is true when you're trying to charge your phone. You want your phone to charge as quick as possible. You want to get as much electricity to your phone as you can. So you want to have these wires with the smallest possible resistance. You have a extension cord that you're using outside, maybe to power an electric lawnmower or electric weed whacker or hedge trimmers. You want it to have the smallest resistance possible. You want to get your energy to that appliance. Okay, so under what circumstances would you want to have moderately high resistance? They would be things like in your toaster, in your hair dryer. You want to get the electricity to those devices efficiently, but inside the toaster, inside the hair dryer, you want to have a moderately high resistance so that you can generate heat. You don't want the electricity flowing through too easily. You want to turn some of that electrical energy into heat. Later, we will learn exactly how to figure out how much resistance we need to generate what we're looking for. But you'll find these wires have a lot more resistance than the wires that are bringing the electricity to the toaster itself. Okay, so what are the factors that affect how much resistance we're going to experience? One of the factors is the length of the wire. Longer wires have more resistance. If you double the length, you double the resistance. The length should be measured in meters, not feet. The next factor that affects resistance is how thick is the wire. if you were to slice the wire and look at a cross section of that wire, a little circle as you cut through the wire, the area of that circle affects how much resistance you're going to experience. A bigger area means less resistance. A bigger area means there is more room for the electrons to flow through that wire. You're going to be able to get more electrons through the wire per second than you could with a thinner wire. Okay, that area should be measured in meters squared. Okay, and again, with our toaster, the reason why they have more resistance is because of the material that they're made out of. Generally speaking, they would be made of something like nichrome, something that has a higher resistance than, let's say, copper or aluminum. Okay, so our three factors are the type of material, the length, and the area, the cross-sectional area. Here you can see a hair dryer, and you'll notice that there are two different sets of wires. One of the wires is thinner than the other. This is because there's two different settings on the hair dryer. Okay, one of them is going to have more resistance than the other. So again, we're looking at three factors. What are the wires made out of? How long are the wires? And how thick are the wires? Now with car battery, you need them to be kind of long or they're not going to reach from car to car. But if they're excessively long, they're going to have more resistance and not do as good of a job. Okay, so here are the three different factors side by side with wires. So you can see length. This one has less resistance because it's smaller, it's shorter. We have material. Okay, this one has less resistance because it's copper. The other one, being aluminum, has more resistance. And finally, we have two wires of the same length. They're both made of copper, but one of them is thicker than the other. Again, the better one is the thicker one. Three factors: length, area, cross-sectional area, and material. Material goes by the letter rho. It stands for resistivity, and each material has its own unique resistivity. They are found on one of your reference sheets. So look for the reference sheet that says resistivity. Okay, the chart will look something like that. I would recommend putting the rho symbol right above that chart so you remember. Smaller numbers, less resistance. Bigger numbers, more resistance. Okay, so when you want things to have resistance, you're going to use things like nichrome or graphite. When you want to have the electricity travel through it easily, it'll be things like copper. If you have the money, you can even go silver and it would travel even better. Notice gold is not the best, but gold has some unique properties we'll talk about later that will make it desirable in some applications. Okay, and then we have aluminum and tungsten. Tungsten is the material we would find inside an incandescent light bulb. Okay, the filament in there is made of tungsten oftentimes. So we have length, we have area, we have material. Here's what the formula looks like. R, capital R, is resistance. It's measured in ohms. This comes off of your reference sheet. This is in meters based on the length of the wire. And this is area. Most times your wires are going to be circular in cross section, so the area is pi r squared. Okay, so in lab we kind of messed around and we played around to see how this would work out, and we saw bigger wires, thicker wires had less resistance. However, when we measure the thickness of wires, oftentimes it's done in a very strange way. So I want to take a moment and make sure you understand this. It is called gauge. Okay, it was a way people used to describe the thickness of the wires way back in the day. And you'll notice this is actually a little tool that will be able to tell an electrician what gauge the wire is. So they would strip the wire down so all they saw was the metal, and they would see which of these holes it fit in. And the last hole that it could fit in would be the gauge of the wire. You'll notice 0 gauge is quite big, and as the numbers get higher, the wires get thinner. As the numbers get higher, the wires get thinner. So when you buy jumper cables, oftentimes they will tell you the gauge of the wire. Lower numbers are better. Lower numbers mean it's a thicker wire, meaning it will have less resistance. I put this on our Google Classroom so you can print this out. This would be very helpful to have. This tells you the diameter of each of your different gauge wires. Okay, so at this point I want to make sure you understand the best combination of wires. So if you want to have a wire that's going to have really low resistance and is going to last for a really long time, what you want to do is make the wire itself out of silver. Silver's best. If you can't do silver, you do copper. They are the two best materials. However, both silver and copper can oxidize. So if it's underneath of a plastic or rubber protection, that's great. Silver's great, copper's great. The bad part is the ends that are exposed to the air and can oxidize. You want to have those gold tipped, gold plated. Gold is not as good in terms of resistance properties, but gold does not oxidize like the others will. Gold will maintain its shininess and its low resistance when exposed to air. So the best combination is silver or copper inside, gold any place it's exposed to the air. So if you're doing any kind of high-end audio and you want the best possible connections, that's what you want to go with. Silver or copper inside, gold on the outside. Okay, so I'd like you guys to see how you actually calculate a resistance. Okay, so you're going to take your resistivity. This is nichrome, and that is going to go in here. The length, make sure you're in meters. That's going to go in there. Finally, the area, this is the tricky part. You look up 32 gauge wire. It says it's got a diameter of 0.202 millimeters. You have to cut it in half to get your radius. You then have to change it into meters by dividing by 1,000. And finally, you put it into the area equals pi r squared equation. Combine it all together and see if you can get the resistance of this wire. Okay, so I hope you understand better the 3 factors that affect resistance, how to get the best wire for your application. Sometimes you want low resistance and sometimes you want high resistance. Finally, I hope you can follow along and calculate the resistance of an actual wire.